Okay, so let's start. It's my pleasure to introduce Dima Noshchenko from Dublin Institute of Advanced Studies. Unfortunately, Dima didn't get a visa, so we have to go in a hybrid mode. We hoped to really have you here in Warsaw, but there is also a good side that everyone can join, and we hope for a really good recording with this virtual board. So the virtual floor is yours, and I guess that today will be about symmetric quivers and motivic generating series.
Thank you so much, Piotr, and thanks a lot for everyone who is joining today. And the goal for this lecture series is basically to make you familiar with some new developments in quantum topology and various adjacent fields. And for today, I planned to speak about symmetric quivers, just some basic definitions, and to arrive at motivic generating series, and if time permits, to study some properties of transformations of such series. And yes, so the starting point, symmetric quivers, you can just think of it as a collection of nodes and arrows, such that you have the number of ingoing arrows equals to the number of outgoing arrows. So here is an example. Can you see my pointer, by the way?
Yes.
I guess you can, yeah. So here you have a quiver with 4 nodes, which are denoted by blue. And the arrows, we also allow for loops. And the number of loops can be arbitrary. So basically, all we need for such a quiver is the data that is encoded in adjacency matrix, which we usually denote by C. And the only requirement is that C is symmetric and filled with non-negative entries. This is for today. And here, for example, you can put like 0, 0, 0, 1, and 2. Well, then you put accordingly the number of arrows. For example, if this is the number 1, this is number 2. So you can put any ordering of the nodes. This is number 4. Yeah, so then you can just start to fill this matrix according, for example, 3 and 4. So here would be 2. Oh, sorry, here it would be 1, not 2. So one can just simply think of such queries as combinatorial objects, and why we are eventually interested in such objects is because there's a very rich structure, and we want to define some Q-series, a generating series based on the quivers, and let me just proceed with derivation of such a Q-series. For today, I thought that maybe the best way to do this presentation is just the most down to earth would be to consider quiver representations over finite fields. And so we consider quiver representations, and by representation we mean that to every node of a quiver, we must attach vector space, a finite dimension, and to every arrow, we must attach some linear map between the corresponding vector spaces. So, a representation would be a collection of objects like this. So we have vector space Vi and the map to Vj. So for every ij, which belong to the set of quiver nodes, and the set of quiver nodes we usually denote by Q0. And the set of arrows we denote by Q1. So yeah, so imagine that you have, like for example, in this quiver, you have some collection of vector spaces, and in particular, so one can attach a dimension vector to such a representation, which we denote by letter D. So this is a vector, and it will be just filled with dimensions for every vector space that we have here, from D1 to Dm. In particular example, here m equals to 4 in this quiver. So you can think of this vector as running through all values which are non-negative. So this could be the M field with non-negative entries. Yes, so this is the basic data, and now we want to make some specialization. So namely, we do not want these vector spaces to be arbitrary. Well, so far we only consider that they are finite dimensional, but now let's make the most simplest case possible. Let's just make a representation over a finite field. So we consider a finite field F. Yes, a finite field. So F is fixed as F of Q. So this is just the Galois field, and basically it consists of Q elements. So as a set, it is just a collection of Q elements, so 0 from 1 and Q minus 1. And well, usually, yeah, so if you want to fix Q is some prime number to power, to some integer power. Yeah, this is that. Yeah, and so now, given that, basically we can study a representation space. So the next thing we consider is a representation space. And this object is defined just by arrows of the quiver. So I will use the letter R to denote such a space, and this is given by a direct sum over all arrows of the quiver. Now alpha belongs to Q1, the set of arrows, and we just take all these linear maps. So basically, these are matrices of size di times dj. Where is that? Yeah, so here we have a matrix of size di times dj. So given that the arrow alpha is indeed an arrow from I to j, and yes, this matrix is now, of course, over a finite field. So the entries are, so basically there are only finitely many combinations of entries that you can put in these matrices. They're given by this set from 0 to q minus 1. And now let's count the size of such a space. So, by the way, if you have any questions, so at any moment, please feel free to interrupt and to ask questions.
I have a question about this exponent and this prime to the exponent. Is it why do we want this form in this finite field and not, for example, the product of two primes?
Well, in principle, yeah, I think this is not very crucial, but just to make the product in f of q to define nicely, just require it to be like some, well, but yeah, basically this this is more or less like just our arbitrary choice, which does
we
not
don't
reflect.
have problems with multiplication there.
Yeah, so this is just for consistency of this multiplication. Yeah, so for us, it's more crucial that there are only finitely many elements. So basically that you can put in this matrix. So because the next step that we want to do is to compute the size of R. And well, you can try to see. So basically, what is the size of R? So let's do some very simple examples. So for example, let's take just one node, a quiver with one node and 0 arrows and loops. So in this case, yeah, so in this case, basically you have a zero-dimensional representation. And basically the only map you consider is like zero map, so maps from 0 to 0. So in this case, the size of R is just q to power 0. Just 1. So this is just trivial. So in the next case, we can consider, for example, like this. So now we have a map, and so the claim is that in this case, the size of R is q square. Q to power d square. So d is the dimension of a vector space, and we consider just some automorphism of this vector space. So since we work with finite field, we only have finitely many possibilities, and to describe such a matrix, so basically this is the given one single matrix of size d times d, so this is how many entries you can put inside. So similarly, well, you can just continue to kind of generalize this formula, and I will give you the final answer. So in arbitrary case, this formula is given by q to some exponent. An exponent is given by summation over ij from 1 to the number of nodes to the size of q0. And here we have Cij times the idj. So this is the quadratic form. So this is the part of the Euler form of the quiver, basically the summation over all entries of adjacency matrix. Yeah, so this is one part that we want to keep in mind. And the second part would be the following. So we also can consider the action of GLM on such a space of representations. So here on R acts GL. Well, I can just make this kind of symbol, but this would be the summation, of course, over all vectors. So this is the copies of GL of DI over this finite field. And this summation over all i's, all nodes of the quiver. And how explicitly this action is defined? Well, what we can write is that we can write conjugation of matrices. So essentially, if we have some, let's say we have a pair of nodes, and if there is an arrow alpha, and going from I to j, so what we can write is that, okay, we have a pair of vector spaces. So we have vi, here we have vj, and so since, well, this is slightly abuse of notation, but usually in literature on quiver representations, people also use v for both vector spaces and linear maps. So here v alpha denotes the linear map between Vi and Vj. And so this guy, GL, acts on V alpha just by conjugation. So we have element Gj inverse V alpha Gi. So where Gi and Gj belongs to this guy, GL. So this is the action by conjugation, and now we want to, well, maybe now what we can do is just to compute the size of this group GL. Yes, I can go here. Yes, so now the question is, what is the size of GL? And this can be estimated as follows. Yes, basically now what we have to do, we have to count. So let's assume that we have some matrix, so an element of this group, and let's take the first column. So now what is, so we're gonna think what is the requirement for this first column. So given that we must, yeah, we must have determinant not equal to 0, of course, and elements from the finite field. So now the first column, of course, is so the number of possibilities. To put it here is would be just QDI minus 1. So QDI means that we can, of course, put all elements from Q to Q minus 1, and minus 1 means that we exclude the possibility where all vector is identically 0. Of course, this is excluded. And assuming that, so now we ask, so what is, how about the second column? So how many possibilities are now here? So now we also have to take into account not only the fact that we exclude the 0 vector, but also that here we need to exclude linear dependence on this first vector. So yeah, essentially the number of possibilities would be equal to QDI minus Q, yeah, just minus Q. And so similarly, if one can continue like going all the way to finish this matrix, the one arrives at the formula which looks as a finite product. Yes, so this is just number of possibilities for the first column, which was Q to power Di minus 1 times, for the second column, we exclude the first column, and so on. And the next, so the finally, it would be Di minus Q per Di minus 1. So this is the size for GL. And now we can also rewrite it in a slightly different way. But so we can introduce the Kupak hammer symbol. Yeah, so this guy is given by the formula. So this is the function of x and q. So two variables and indexed by n, and this is just the product from 0 to n minus 1, remain minus x q to power k. And so given that, can now rewrite the size of GL. Yes, so this would be given as minus 1 to the I. So I just take out some of the factors of Q and write it in way that we would like to have. So this is di square minus d, and this is divided by half, and times q per hammer qd. And here I have to put the index d. So this is like for one copy of this GL. And sorry, I have also, of course, to put this index d here. So now if you want like the size of the whole GL, so then we have to take essentially the product over all the i's. So we take this function and we take the product of over the I. This would give the formula for the whole group GL. Yeah, so this is the second ingredient. And now we want to rewrite, to rewrite this formula in a slightly different way. So just now we have general arguments. So the size of GL would be given by, so I will write it first and then I will comment. So this could be, so given a V representation of a quiver, so we can consider the orbit of this representation by just acting simultaneously by conjugation on all elements and just continue acting. So this defines the orbit. This is the orbit of V. And now some representations would be stable. So it means that there is some set so there is some set of elements such that basically this acts on the representation itself and gives again V. And one can now write the size of GL as the product of these two guys. So one is the orbit and the second is stabilizer of V for any representation. So one can, in principle, fix your favorite representation and compute for such a representation to compute the size of GL. And of course, it does not depend on the choice of V. And so now we can, what is the next step? So the next step is just we have this GLV. Sorry, I want, I would rather want this guy here, and I want to just to express this is just GL divided by GLV. But on the other hand, so recall that we had this representation space, and the size of representation space, it could be written essentially as a sum over equivalence classes of over representations, and so this formula holds. And so basically what we do here is that, again, we take a representation, so compute its orbit, so we start to act by conjugation on all vector spaces, or sorry, on all linear maps that we have inside this representation. So this defines an orbit, and we compute the size of this guy. And now we, of course, have to sum over all equivalent classes of non-equivalent representations, essentially. And this gives you the size of the whole representation space. And so since we already computed like both guys here and there, so now we can safely say that so what we essentially have is that if you take R and divide by GL, so now this guy is, this now is what we want to study. So this is the sum over V. Right, and this guy we want to yeah, usually it is defined by this letter S and labeled by dimension vector. So we can now write what is it explicitly. So the claim is that now we have, just write again, so R divided by LV. Oh, no, sorry. Not V, of course. This is just the whole group. So we don't fix a representation because we sum over all such representations. Yeah, so this is just so in denominator we have the product of cubic hammers, and in numerator we have this exponent Q, the sum Cij divided J. And we also have some piece which come from, again, from the size of GL. So there will be some, well, there is some minus sign. And there is some Q to some quadratic power. So, but eventually we want to get rid of all the rest, and we want to write now the generating series that we wish to study is, yeah, so now basically the main definition for a clear generating series. Which we denote by letter Q, by letter P, sorry. So it depends on some number of generating parameters, x1 up to the size of the Q xm, also Q, and now we insert basically this expression that we have here. But we want to sum it over all dimension vectors, d1 to dn. And what we also want to put this minus sign inside here. And the second thing that we want to consider, we want Q go to Q square. So we want, instead of Q, work with squares of Q. So this would be very important when we study like not invariance from Qs and other things. So the final expression that we end up would be here just Q squares everywhere, d1 up to the m. Yeah, and here would be minus, which we put inside here the summation. And we did something else. So since we slightly transport the matrix, let me just put here Cij tilde, dij j up to n. And yeah, all this thing. Oh, let me just maybe erase this part. Yes, all this is multiplied by generating parameters x1 to power d1 to xn to power dm. Yeah, and here all the chunk that has appeared from denominators, we essentially can some part we put inside Cij and some part we absorb into x's. And this is the final object, basically our main definition that we want to study. So we want to study this generating series. Yes, maybe have any questions on derivation, or is it more or less clear? All right, so yeah, so philosophically we slightly changed the notation here, but so when we write a quiver, so we usually speak about quiver generating series whenCij's are exactly the same as those for adjacency matrix. So here in above example, it wasn't exactly the case. So here, because there was some quadratic shift that you might recall was here. So essentially the difference, the main difference between this expression and this expression is that one here uses the Euler form of the quiver in the exponent of Q, and the second one just kind of absorbs this additional Q di square and absorbs into Cij, and we simply say that if you have a quiver, so if you have a quiver Q, like again with some of nodes and arrows, so simply let's write Cij as the adjacency matrix and just let's write this object where you only have in the quadratic exponent, you have this Cij without tilde, so tilde I will erase. And from now on, just let's think about like this correspondence between quivers and generating series. Yeah, of course, it's not the only way that we can define a quiver generating series. So it also bears the name motivic generating series, but I would not say much why it is motivic. So the name comes from Lefschetz motif, but there is some slightly more general derivation of the series. So in principle, you don't have to study representations of a finite field. You can study more general representations, but this is just gets more technical. And yeah, for the purpose of these lectures, I will not go there. And yeah, so basically, we can continue with this object here. So yeah, now I need to check something. How can I extend this blackboard? Yeah, maybe I can write here. Yeah, so I can just write the series again. So we ended up definition of a quiver series. So one can now ask, for example, what are the transformation properties of such series? And so let's write cos here. And a vector of generating variables. Yes, so one transformation that we consider, for example, so we can formally consider Cij to be just any integer. And in principle, which also very useful, we work with knot invariants. So it could have like negative entries, both mixed with positive entries. So some, for example, matrix like this would work as well. So in this case, it's very useful to consider transformation which we call framing. And framing is simply, given the matrix Cij, so C11 to Cmm, framing simply adds a constant to every entry of the matrix. So this maps to the same, but plus some constant f. And we take this constant to be an integer. So in principle, we still speak about quivers, even if you have negative entries in the quiver matrix. And one can just say that we add a framing to this formally negative quiver, but you can get to positive entries. However, some properties of such generating series depend non-trivially on framing. And so my next step, so I still have some time for today, and I want to introduce you the product form of the generating series. Maybe let me just erase that. Yeah, so yeah, apparently this takes some time, but yeah. So yes, now we need a product form. And yes, so one can do the following. One can introduce the operator, which is called placistic exponential, as written as a symbol exponent, where f here is some formal series which start with, so it's usually denoted this time. So f of x is essentially some series that starts with x plus ax x square plus aq x cube plus and so on. So these are formal series, but the crucial thing is that the x0 term is missing. For such a guy, we can define the placistic exponential by the formula. So we take a usual exponential and write here the summation from k from 1 to infinity. And we write f evaluated at xk divided by k. And so this can also be rewritten. So now if f of x is here the sum from k to infinity, ak xk, as there was in this example, so then the specific exponential acts in a nice way. So what it does, it transforms the sum into a product. So here the result essentially is a product from from 1 to infinity, 1 minus x k to minus ak. And now the crucial thing is that we can now take this Quivers generating series that we have here, and we can rewrite it using the placistic exponential. So we can write PQ as a placistic exponential of, and now we introduce some notation. So an exponent, we introduce omega q, which is some function of x1, xm, and q divided by 1 minus q squared. And now it's very important. So this is basically the second definition of the Quivers series, where now this guy inside the exponent, this omega q is called the generating series of Donaldson-Thomas invariants. Of Q. So just to finish for today, I will write the theorem. So which have been firstly conjectured by Kotsevich and Soibelman. And proven by Yefimov. So this was in 1220. This was like 1220 and around 2009. So yeah, this states that omega q can be written as a series some q to power s. Here is some number q which depends on the dimension vector, and this everything is multiplied by x to power d1 xm dm. But so far this is not really interesting, but the thing which is interesting is that, well, essentially the statement of the theorem that these guys, there are non-negative integers. So this belongs to some non-negative set of non-negative integers. So this is the crucial statement of the theorem, because it is not manifestly obvious that these numbers should be integer for any symmetric Quivers, but there are, and this is very important because in physics, these numbers, they're also obtain interpretation as some count of VPS states in gauge theories, and these numbers also have very important interpretation when we speak about knot invariance. So then there are many different connections, different topics. Yeah, so I think for today I'm out of time, and Piotr, I'm not sure if I can.
Yeah,
maybe I can.
We are slowly approaching our limit. Maybe there are some questions. So you can. Do you have questions? Maybe also some people in on Zoom would like to ask something. You can unmute yourself. Okay, so I guess we can finish for today. Let's thank Dima so we can hear it.
Yeah, thank you so much.
Yeah, thank you. I will stop recording.